Welcome to all. In this video, we will see the concept of process synchronization. A cooperating process is one that can affect or be affected by other process executing in the same system. Okay, the cooperating process may either directly share a logical address space, or you can say that both. It is something like both code and data. So whenever we talk about system, definitely for any applications or any process, or it may be anything, so there will be some set of codes, as well as there will be some set of data which is being transmitted from one end to another end. So by considering both, we are thinking about this. So it is allowed to share the data only through files, so that also possible. So ultimately, this is something like cooperating processes. This is the concept involved in cooperating process. Okay, a system consisting of number of cooperating sequential processes, all running asynchronously and possibly sharing data. So whenever we think about a system, so there will be a chance of transferring the data from one end to another end, or from one process to another process. So if I want to give a simple example, we can think something like this. So whenever you plug in an USB device to a particular system, definitely there is a concept of transferring the data from one device to another device, isn't it? From one hardware device to another hardware device. So USB can be considered as a hardware unit or hardware device, isn't it? So it is a separate it is a portable device, USB drives, isn't it? In the same fashion, even laptop will be having its own benefits, and it can be portable, and it is a separate hardware device. So whenever we copy the files, or whenever we try to transfer the files from either from laptop to USB, or from USB to laptop, definitely there is a concept of sharing of data or transferring of data. I can say, instead of saying sharing of data, it is better to say transferring of data from one end to another end, isn't it? So it is kind of process, because even each and every transfer, each and every application we are running in the system will be having its own ID. And it can be a thing like it can be I can say it can considered as a process, isn't it? So definitely there will be having its own ID, that is nothing but PID. So there is a concept of transfer of data from one process to another process. So that is nothing but cooperating process, or there has to be some cooperation between the process for the transfer of or exchange of data, I can say like that. Okay, there is a concept of a critical section problem. Okay, so this is one of the essential information which you have to understand with respect to operating system. Okay, consider a system consisting of n process. So let us consider like p0 to pn minus 1. So say there may be having 10 process, or 20 process, or 50 processes. Depends. Okay, it depends on the particular system. Each process has a segment of code called critical section. So each and every process will be having a concept of critical section. So you have to remember in something like that. It's a segment of code. Critical section is nothing but segment of code in which the process may be changing common variables, updating a table, writing a file, and so on. So whatever the update, whatever the changes we do in a particular process, that will be updated, or that will be stored, or that will be it is something like a log file, isn't it? So for whatever the updates we do, we usually if I consider the real-time example, you manually write it down, correct? In the same fashion, with respect to processes, there will be having segment of code. That segment of code is called critical section, and it mainly deals with the updation of things, or table, or writing to a file, something like that. Okay, so the important feature of the system is that when the one process is executing in its critical section, no other process is to be allowed to execute in its critical section. That means whenever you are trying to execute, or accomplish some tasks, so if that particular process is inside that critical section or segment of code, that in that time, any other process, whatever it may be, the priority, or it may be anything, it cannot come and access that particular place. That is the meaning. Okay, so that place is nothing but that section or critical, that area is called critical section, or that segment of code is called critical section. The execution of critical section by the process is mutually exclusive in time. So that is one of the important thing you have to understand. So whenever we are executing some the processes which are in critical section, they are mutually exclusive. Fine. Each process must request permission to enter its critical section. So that also one point. It is better. So I thought of giving the things in with respect to points instead of going for entire paragraph or like half page or one page. It is better to condense those information, and I can put that information in a point wise thing. So it is better for you to remember as well, to update yourself as well. Fine. So each and every processor should and must ask the permission to enter the critical section. The section of code implementing this request is called entry section. So that is one point. And another point is critical section may be followed by an exit section. So definitely whenever we talk about critical section, there are two concepts. One is entry section and another one is exit section. So you can think of this body. Okay, in terms of code they have gone for. So there is a do while loop. Inside the do while loop you have two sections. One is entry section and the second one is exit section, but in between that you can write some segment of code, isn't it? That is nothing but critical section. And at the end, after the exit section, there is a concept of remainder section. If there any concept which are remain, fine, or which has to be executed explicitly, that kind of code can be written after the exit section. So it is while of one or while of true. Until and unless you want to run that loop, you can go for it. Once the condition fails, you are coming out of the loop. That is the meaning, isn't it? So this is the block diagram, or this is the kind of block you have to remember whenever we talk about entry section and exit section or critical section. Fine. Now the next thing is a solution to the critical section problem must specify the following three requirements. Okay, so now we have to think about the solutions. Like there may be some problem with respect to critical section, isn't it? So something like if one process is already running or already present in critical section, then other process has to wait, isn't it? There may be a wastage of time, there may be a problem with respect to performance, there may be a problem with respect to frustration of a particular person, because if the system is not responding with a greater speed, definitely we will not feel good, isn't it? That's why. So the requirements are, there are three requirements mainly: mutual exclusion, progress, and bounded waiting. So first one is mutual exclusion. If process P is executing in its critical section, then no other process can be executing in their critical section. So that is nothing but mutual exclusion, isn't it? So if one person is in action, then rest of the people or the rest of the process has to be waiting. There is no other option for the sharing of critical section. There is no such options. Okay, the next thing is progress. If no process is executing in its critical section and some process wish to enter their critical sections, then only those process that are not executing in their remainder section can participate in the decision on will enter which will enter its critical section next. So ultimately the meaning of this is, so whatever the process which are trying to enter to the critical section or their own critical, see each and every process will be having its own segment code. That segment of code is called critical section, isn't it? It is not like a general area or public area where any process can come and execute. It is not like that. So each and every process will be having its own. Okay, correct. That section, in that section this process will be executing. Fine. Now if they with after the permission only they can enter the critical section, but in between, if no processes are executing in the present era, and then if any process try to wish to get into the critical section, then what is the thing, then they have to go for the remainder section. They have to participate with actually whatever this processor which are process or code which is participating in a remainder section, that can be entered. Okay, you have to remember like that. Now you may get the doubt what you mean by remainder section, so you have to remember this particular thing. Fine, this block diagram. So after the exit section only, you will be having the concept of remainder section. So these things are with respect to codes. Okay, so they have given the concept with respect to one box, but ultimately programmatically if we think, so it is nothing but a set of code. Okay, so that set of code will be executing, and based on that set of code only you will be working on processes. Okay, that is the meaning. So that is nothing but progress. The third one is bounded waiting. There exists a bound on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section, and therefore that request is granted. So that ultimately that means bounded waiting is nothing but, so as I said, one process, if it is in its critical section, no other process can access that particular critical section, isn't it? So rest of the thing has to be waiting, isn't it? They have to wait to get into the critical section. So that is the overall idea, you can think of it. So whenever we talk about critical sections, fine. So that is one thing. The second thing is, so there is a separate solution. Okay, two process solution. Now let us see what you mean by two process solution. Okay, now we restrict our attention to algorithms that are applicable to only two process at a time. Okay, the process are numbered P0 and P1. Okay, P0 or P1 or P0 or P1. Fine. Now for convenience, when presenting Pi, we use Pj to denote the other process. Okay, so one process can be represented Pi and another process can be represented as Pj, and there is one thing, so j equal to I minus, 1 minus I. You have to, that is a one statement they have given. So whenever we deal with respect to algorithms or programmatically when we are dealing with the critical section problem, so these notations are required. Okay, our first approach is to let the process share a common integer variable turn initialized to 0 or 1. So it is better, it's something like a flag variable, isn't it, just to make sure that the things are working fine. So based on the flag variables, based on the values which are assigned to the flag variable, we can come to a conclusion that what kind of things are happening in the system. The same concepts are available in this particular algorithm as well. Okay, if turn equal to I, then process P is allowed to execute in its critical section. So turn is nothing but it's a kind of flag variable. I don't know how many of you know about flag variable. See, flag variables are nothing but, so based on the values assigned to flag variables, we are taking some decisions. If I want to make it very clear or very easy, I can say something like that. So if you are going in traffic, if there any in the signal, if you are seeing red light, it is automatically mean that you have to stop your vehicle right there, isn't it? When it becomes green, you are allowed to move forward. In the same fashion, so instead of going for signal lights, that signal lights are considered as a flags in a programming, something like that. Okay, if it is 0, then don't do the work or do the work. If it is 1, do the work or don't do the work. Or it is something like vice versa. Okay, so if it is 0, if you set the code something like this, if flag equal to 0, you have to check. If flag equal to 0, then perform some work. If flag or if something like if flag equal to 1, then you should not do the work, something like that. Okay, so just for the identification purpose, we are using flag variable. In the same case, instead of using flag word, they have gone for turn. Okay, the structure of process Pi is shown below. So shown that the last line, the last part, instead of going for last part, let us complete with respect to theory part. This solution ensures that only one process at a time can be in its critical section. However, it does not satisfy the progress requirement since it requires strict alteration of process in the execution of the critical section. So they ultimately talk about the critical section with respect to this particular algorithm, but you have to remember this. So it is not satisfying progress requirement. Progress requirement is nothing but we have in the previous slide we have seen total 3 requirements, isn't it? One is a mutual exclusion, second one is progress, third one is bounded waiting. So in those 3 requirements, that progress progress requirement is not getting satisfied with respect to algorithm 1. For example, if turn equal to 0 and P1 is ready to enter its critical section, then P1 cannot do so. Okay, even though P0 may be in its remainder section, it is not possible. Until and unless it finishes everything, P1 process cannot access the critical section. You have to remember this. Fine, with respect to algorithm 1. Now we can see the algorithm 1 how exactly they have gone for with respect to code. So do while loop, again inside the do we have while loop. Turn is not equal to I, then you are allowed to go to critical section. Okay, turn is nothing but one flag. The turn will be initialized to 0 or 1 based on the number of process. If something like if turn equal to 1, that means some processes are using the critical section. If turn equal to 0, then no process is using the critical section, something like that. It is for identification, id value. Fine. Now turn equal to j, remainder section. So you have to initialize the j value to turn and you are going for the remainder section, and it is while of 1 or while of true. So until unless condition fails, you are inside the loop. You have to remember something like this. So it is just a general algorithm, it is not a special thing here. So it is just an algorithm. So you have to see the concept how exactly algorithm 1 is working. Fine. The second thing is algorithm 2. The problem with the algorithm 1 is that it does not retain the sufficient information about the state of each process. So it just check the flag, or it will just check the turn variable, and it will decide whether it has to, the process has to go to remainder section or critical section. But with respect to algorithm 2, what they are saying is it remembers only which process is allowed to enter the critical section. That is what just now I said. The remedy for this problem, we can replace the variable turn with the following array. Okay, boolean flag equal to so now say they have talked about flag variable. Okay, flag array. Okay, it is nothing but turn array. Everything is fine, you can give any variable name, but ultimately it is something like identifier. Based on that, we can take some appropriate decision. That is the deal. Okay, the elements of the array are initialized to false. If the flag of I is true, this value indicates that Pi is ready to enter to the critical section. So flag of I is nothing but it may be flag of 0 or flag of 1, because total 2 variable boolean variable isn't it? So it can be true or false. So if it is true, then that means that process is allowed to critical section. If it is not true, then definitely it is not allowed. It's something like that. The structure of the process Pi is shown below. So they have gone for one code there, do while loop. Again, inside the do, you have flag of I equal to true. So you are initializing I with the, or flag of I position with true value, while flag of j, if it is true, then go for critical section. If it is not true, directly come out. Isn't it? So now again you are overwriting flag of I equal to false. Once it is done with the critical section, then flag of I should be initialized to false for the next, sorry, not for the next. So it means the still that particular process is taking the action. It is in the action, because flag of I, when flag of I becomes true, then only other processes are allowed to take the critical section. That is the concept of algorithm 2. Okay, you have to see this particular algorithm. That's it. You have to remember how exactly it is working as of now. Fine. Now you have the concept of algorithm 3 also. By combining the key ideas of algorithm 1 and algorithm 2, we obtain a correct solution to the critical section problem, where all 3 requirements are met. All 3 requirements are nothing but mutual exclusion, progress, and bounded waiting. The process share 2 variables. So again you have the concept of boolean data type, to one array, flag array, and there is one integer value called term. Fine. Initially flag of 0 equal to flag of 1 equal to false. So by default you are setting the complete array to position with the false value. Okay, and the value of turn is the immaterially, or instead of going for immaterially, we can say it is initializing. We are going to initialize turn value with the 0 or 1. Okay, the structure of the process pi is shown in the figure. Okay, there is a concept of figure, that is nothing but one algorithm. We will see in the next slide. To enter the critical section, the process pi first sets the flag of I to be true. Why you are going to change the value of flag of I? It, see, you have to remember one thing, guys. Okay, so it is all about programming. Ultimately, this process synchronization or any kind of problems, it can be written in C or C++. There will be some set of codes. Okay, that is the reason why they said there is a concept of segment of code. That segment of code is called a critical section, theoretically. But programmatically, when we think, you may be wondering, if you are very good at programming, definitely you will be having one doubt. What do you mean by flag of I? What is the value of I? Which index is being referred? If the sir is explaining like this, how exactly we can understand? Definitely you will ask, isn't it? Now these explanations are good, or explanations are better if you understand only programming. It is something like I can be anything based on the for loop, separate for loop. They are not giving the entire code here. They are teaching, or they are giving the information how exactly you are doing with respect to algorithm 3. They are not giving the entire code. Remember this. Okay, if you are little bit good at programming, definitely you will ask this question: flag of I means what, sir? Which index is being referred? What is the value of I? Isn't it? If you are programmatically good, definitely you will ask this question. But here in this explanation, what they have gone for, they have just said that flag of I is true means you are allowed to give the process to that particular critical section. Now definitely you will be having the question, what do you mean by critical section? What kind of code is present in critical section? What is flag of I? What is the value of I? What do you mean by flag? What is turn variable? Isn't it? You will be having these many doubts, isn't it? So, but they have gone for the explanation with respect to programming level. Fine. But they did not give the code. Definitely they did not give the code in the textbook also. They have just given one snippet, which is not at all sufficient. But the thing is, so if the flag of I means it may be flag of 0 or flag of 1. Okay, because only two positions, memory positions are possible, because while giving the declaration, they have gone for boolean flag of 2. So boolean is nothing but either true or false. Fine. So now if it is true, then turn is then sets turn to the value j. Now there is one more variable called j, and you are setting whatever the value stored in turn to j. Okay, now it may be 0 or 1. Fine. Ultimately you can be storing 0 or 1, and that turn value is stored in j. That is the main thing. Fine, that is the one thing. Now thereby asserting that if the other process wish to enter the critical section, it can do so. How it can do so? By checking the flag of I value. If it is true, then only process are allowed. If it is not true, definitely it is not allowed. Processes are not allowed to get into the critical section. It is as simple as that. Fine. If both process try to enter at the same time, turn will be set to both I and j at roughly the same time. Based on the turn variable only, this flag variable will be set. Not flag variable, I and j will be set. Based on the I and j only, flag will be set with respect to true or false. By looking at true or false, the processors are allowed to enter to the critical section. If both flag of 0 and flag of 1 are set to true values, true, then definitely those two process can be accessed, or that those two processes are allowed to get into the critical section of their own. That is the meaning. So ultimately, with respect to algorithm 3, what you are understanding, it is directly means that two processes can simultaneously access critical section with the help of flag array. Okay, so that is the meaning. Fine, only one of these assignment will last, the other will occur. Okay, but will be overwritten immediately. The eventual value of turn decides which of the process is allowed to enter the critical section first. So immediately, if they are giving, even though sequence simultaneously, the turn value will be set, but there will be a slight delay, and the algorithm should decide that which process has to be given with the critical section, or which process has to enter to the critical section. You have to understand something like this. So now there is some information which will prove that the solution is correct. The first one is mutual exclusion has to be done, the progress requirement has to be satisfied, and the bounded weighting has to be satisfied. So if these three requirements are set, then only you can achieve the solution for critical section. To prove property 1, we note that each pi, or processes, number of processes, it may be any number, enters its critical section only if the flag of j equal to false or turn equal to I. Okay, so that is a code you have to remember. Also note that if both processes can be executing in their critical section at the same time, then flag of 0 and or equal to flag of 1 equal to true. Now why equal the both the flag of 0 and flag of 1 is true? That means based on the true value only, processes are allowed to enter the critical section. If both the places are set to true, that means two processes are using critical section simultaneously. By default, you have to understand this. Fine. These two observations imply that P0 or P0 and P1 could not have successfully executed their while statements at about the same time, since the value of turn can be either 0 or 1, but cannot be both. Fine. So based on the turn value only, whatever the flag value you are going to set, it will be decided with respect to the algorithm. Fine. Hence, one of the process, say for example pj, must have successfully executed the while statement, whereas pi had to execute at least one additional statement, turn equal to j. However, since at that time flag j equal to true and turn equal to j, and this condition will persist as long as pj is in its critical section. Why? What is the meaning of this? So when you are setting turn equal to j, when you are setting flag of j equal to true, that means those two critical sections are busy. That j critical section, or whatever the flag variable, based on that flag variable, the process which are using the critical section, which it is being used, or it will be in action. That is the meaning. Okay, so based on that, mutual exclusion is preserved. Okay, because based on the boolean value, two processes can execute, so can enter the critical section one after the other. Fine. So that is the reason why mutual exclusion is preserved. Okay, so this is the code snippet you have to understand. So there is a do while loop. Inside the do, you have a flag of I, which is set with the value true. Now turn equal to j, whatever the j value, it will set in turn, while flag of j and turn equal to 3. If that is the case, then only processes are allowed to enter to critical section, otherwise no. What do you mean by flag of j and turn equal to 3? Now flag of j also should be 3 and turn also should be 3. Then only you are allowed to enter to the critical section. Otherwise, flag of I will be set to false. Now whenever you are setting flag of I equal to false, that means that particular critical section, any process cannot be entered, because it is false. Ultimately, that means that process pi or p1, or say for example p0, its critical section is busy and no other processes are allowed to enter to that particular critical section. That is the meaning. Fine. Now if that is the case, then you are allowed to go to remainder section. So this will run until and unless the condition get failed. Fine. This is the thing.
Fine. Now to prove the property 2 and 3, we note that process Pi can be prevented from entering the critical section only if it is stuck in the while loop with the condition flag j equal true. If that is the thing, then only we can ensure that the condition is met. Fine. So how it is, the turn equal to j, this loop is only one, is the only one. Okay, so why when flag of j equal true and turn equal to j, that means the condition is true, condition set to true, that means processes are allowed to enter to the critical section. Fine. If p of j or pj is not ready to enter the critical section, then flag of j should be set to false and pi can enter its critical section. Why? Because p of j is false, that means it is busy. Any other processes are not allowed to enter to that particular critical section. Now obviously it will go for p of I, or flag of I position, that process will enter to p of flag of I place, and it will start using the critical section. That is the thing. Okay, now once it is done, then what you are going to do, you are changing the value turn equal to I or turn equal to j. If turn equal to I, then pi will enter to the critical section, because whenever you are going to do that, flag of I will be set to true. Now when you are setting flag of I equal to true, that means pi is allowed to enter to the critical section. You have to remember like this. If flag of j equal to set true, that means pj is allowed to use its critical section, but it is understood, it's a by default thing. Fine. Now if turn equal to j, then pj will enter the critical section. That is what just now I said. However, once pj exits its critical section, it will reset the flag of j to false, so that next process or p of I can be accessed, or something like that. Fine. Any other process which are using can be accessed. That is the thing. Now if pj resets flag of j to true, it must also set turn to I. Why it has to set turn to I? So that next process can access the critical section. Fine. Thus, since pi does not change the value of the variable turn while executing the while statement, pi will enter the critical section or progress with respect to progress after at most one entry by pj or bounded waiting. Fine. Because when the flag of I is set to true, pi will be inside the critical section, then pj has to wait for some time. That is nothing but bounded waiting. But with respect to flag of 0 and flag of 1 or flag array, so based on the true and false value only and turn value, we can ensure that the process can set the requirements of bounded waiting as well as progress. Fine. This is algorithm 3. Fine. These are the 3 algorithms. You have to roughly understand this concept, what you mean by the critical section, what is this flag, and how exactly this mutual exclusion or exclusion or progress or bounded waiting will be taken. So these things are required. Fine. Overall idea is required. So if you have the textbook, you can go and check that in that also, but you don't have the concept of programming in that textbook also. It is a rough idea you have to remember. Fine. If I get any other manual programs or any solution for the programs, then definitely I will put it in the next video. Fine. Now one round robin algorithm is remaining. I will put that video separately. So let me wind up here. You have some other concepts like multi-process solutions and all. We will see in the next class, or sorry, in the next video. So thanks for watching. Okay.